Hi everyone, my name is Jesse Wheeler. I'm a PhD student in the statistics department at the University of Michigan. My advisor is Edward Ionides. I recognize I'm the final obstacle before we can go out and have lunch, so I'll try to be respectful of that time. So today I'll be presenting this paper that was recently published on informing policy via dynamic models, cholera in Haiti. I'll just scroll, I suppose. So the goals of this paper actually align fairly closely with the goals of this workshop in general. In particular, we are interested in a retrospective analysis of an infectious disease outbreak and what kind of lessons did we learn from this system and our modeling experience, and how we can take that to be prepared in modeling future epidemics. So the data we look at are from the cholera outbreak from 2010 to 2019. In 2010, there was a very large and devastating earthquake in Haiti, which already had fairly poor health and sanitation infrastructure. And the earthquake obviously didn't help with that. And UN peacekeepers came to help with the earthquake situation. But unfortunately, with them, they brought cholera infection, or the cholera bacteria, as the working camps for the UN peacekeepers had poor sanitation qualities. So that was how this originated. Cholera is not endemic to Haiti. So for this study, we are going to build off of some nonlinear mechanistic models that were developed by expert modeling teams. Although we are interested in broadly how modeling was approached during this epidemic, we focus on one particular paper by Lee et al. And I apologize, all the names and references are going to be included with the slides at the back. And we're going to focus in particular two models from this study. All right, so here is what the data look like. So you can see at the very start of the outbreak in 2010, there was a very large number of cases, right? They were very much so unprepared for cholera. Quickly, there was some built immunity and some governmental interventions that helped bring down the cases, but it was very persistent for 10 years. So it's kind of difficult to see what's going on in some of these parts. And in fact, if Nick will forgive me, here's a log scale plot of the data. So here we can see a couple interesting things. So there's some seasonality that kind of stands out in this figure once we look at this scale. You can see in certain departments, Haiti has 10 administrative departments, and we have data at each of these locations. So at some locations, there was prolonged periods where there was no recorded cholera. In some of the more populated and larger departments, there was continual cholera transmission throughout this period. But we do see that there seems to be some sort of like negative trend overall. Although, of course, we have large increases in cases, overall the infectious rate seems to be decreasing over time. So we're going to fit the models, treating them as partially observed Markov processes. I think this is pretty well known for many people here, but effectively we have these latent states that are unobservable that describe the system as a whole, and then we have observations that are drawn on these latent states. And some of the key assumptions that we're making in this mathematical setup here is that the latent states have a Markovian property and that the observations are conditionally independent given the latent state values. So given those assumptions, the likelihood function for an arbitrary model can be written down, can be factored into this. And I like to write it down factored in this form because you can see the primary components that are needed to write down any infectious disease system, any partially observed Markov process, that is. So the first is the transition density, which describes how how the latent state transitions from time n-1 to time n. the measurement model describing how observations are taken on the system, and then how the latent states are initialized. So often this can be quite a difficult thing to write down, especially if you want to create a model that is scientifically relevant rather than just mathematically convenient. So our group, we focus on methods that are known as plug and play, or sometimes simulation based, where you only require the ability to simulate from the transition density rather than evaluate from it. So here's the first model that we're going to look at. It's an SEAIR model. It models the data at a nationally aggregated scale. And as you can see, one of the primary questions of this study that we're doing a reanalysis of is how various vaccination strategies might help the cholera situation in Haiti. So we include some vaccination compartments for each of the standard SEAIR compartments in this model. The first thing I'll highlight here, this lambda t, is the transition rate from the susceptible to exposed. And here we allow the consideration of both demographic and environmental stochasticity via multiplicative gamma white noise here in this term. And this is a testable hypothesis, because if you set the variance of this gamma white noise to 0, then you do away with the environmental stochasticity. And we also have a seasonal transition rate. So the transition rate here, beta t, we model as a B-spline basis, a 6 with 6 basis splines. And we include also the possibility of a log linear change in transmission rate just based off of our observation of the data. The second model that we're going to look at is a spatially explicit model. So it's an SAR3 model where the R compartments help with the distribution of recovered rates. It also includes this water component, or a bacterial compartment, where infected and asymptomatic individuals will shed bacteria into a local reservoir, and then that reservoir will drive cholera infection. So this model is spatially explicit for each of the 10 administrative departments that we have, and each department can have parameters that are shared across all 10 units, but then there's also parameters that are specific to each unit. So in total, there's around 34 parameters for this model. Again, we're going to allow for both demographic and environmental stochasticity, and this is the rate of infection as I described. All right, so previously I mentioned we use methods like the particle filter to fit and evaluate these algorithms, but it's well known that the approximation error of the particle filter scales exponentially in model dimensions, so it's not well suited for spatially explicit models. And that was true in this case as well. We found that the particle filter did very poorly on this, just very high variance. So briefly, I want to introduce the block particle filter. This is an algorithm that was developed by a group before this study, and the idea is that you can partition each of the spatial units into separate blocks on this idea of decaying correlation, right? If you have a model structure that has some spatial connections between units, spatial units that are far distance from each other are likely to be less correlated than those that are close to each other, right? In a completely uncorrelated system, you can just do a particle filter on each of the spatial units and you're just fine. So we're trying to take advantage of the fact that if you just do a particle filter for a small part where there's a large amount of correlations, then that should help avoid the cursive dimensionality. So in fact, it does do this, but it does introduce some small amount of bias. Rebskeedy and Van Handel, they derived a bound that's uniform in both time and latent space dimension on this bias and the variance. And in their paper, when they're talking about some of the theoretical properties of this, they actually mentioned that it's primarily a theoretical concept rather than practical. But it turns out that it's actually a pretty practical method as well. So in a previous work by a fellow student in our research group, he was working on developing some high-dimensional filtering methods, and a reviewer mentioned, hey, why don't you try the particle filter? And on the suite of models that he tried all the methods, it turned out that the block particle filter outperformed practically everything else, even though that was a bit of a surprise to us. But since then, it's been used in various studies for metapopulation modeling. So we fit Model 2 using this, an iterated block particle filter, which effectively, if you're not familiar with iterative filtering, you treat the parameter space, or you take the parameters of the model and you treat it as a random walk as part of the latent state, and you do this iteratively while decreasing the random walk perturbation, and you can prove that that will eventually converge to the maximum likelihood estimate. All right, so this section I think is actually the main crux of the study. Now, I realize I'm short on time here, so I'll try to go through it briefly. But talking about model evaluation and refinement. So often, what we found, we did a literature review of all modeling studies with cholera in Haiti. We found some 80 studies, and in them, the primary tools that people use to assess model fit are typically very subjective, or they're comparative, right? So often you'll fit a model, you'll plot data or simulations from your fitted model and try to compare that to real world data, but that comparison can be very subjective, or they're comparative. So you might propose 3 different models and you can pick the best of those 3 models based off of some information criteria like AIC, BIC, or etc. However, these comparisons, again, aside from just being subjective, they don't tell us the relative performance. You might fit 3 really bad models and you could pick one that's better than the rest of them, but does not necessarily imply that it's actually a good description of the system. So we recommend finding a way to calibrate this relative comparison that's fairly common. So one way to do this is via a benchmark model. And here for this study, we used kind of an autoregressive negative binomial model. So here the observations have a mean with the intercept alpha and this autoregressive component beta, and then the overdispersion parameter. And this is quite a very simple statistical model, right? So the idea is if you compare something like the likelihood, or AIC, which adjusts for the number of parameters in a model, and you cannot do better than this very simple statistical alternative, then that might tell you some weaknesses in your fitted model. So in fact, we took these original models that were fit by these research groups, and they did in fact do worse than this very simple statistical alternative, and not just worse, but they did much worse than this very simple alternative, which leads to trying to find some model refinements. So in a likelihood-based framework, we can do this by doing formal statistical tests. So one thing that we added in our model was the environmental stochasticity. That was not present in either of the models previously. Here we're calculating Monte Carlo adjusted profile confidence intervals for the overdispersion parameter that enables the environmental stochasticity. And we find in both models highly favor having this environmental stochasticity versus not. And this is not an idea that's entirely new. A lot of studies have demonstrated the importance of environmental stochasticity in your models previously, but here we find that is also true in both of these models that we considered. Also, you can, when you find that you have a poor performance relative to some benchmark, this encourages us to do a kind of a residual analysis to look why we're performing worse than a benchmark that can lead to some model modifications. So for instance, we found that the data, or the original model, performed quite poorly in this time around 2016, in November or October of 2016. And if you investigate the data a little bit closer, you see that Hurricane Matthew struck Haiti that same week where our model performs really poorly on the data. And when we fit the model without accounting for this additional effect of Hurricane Matthew, the model parameters have to adjust for this really large offsetting impact from the hurricane. So that prompted us to include some sort of mechanism to account for how this hurricane may have affected diseases. So you can see the original model did poorly at this time, but our modified model does a little bit better because it accounts for this mechanism. So I'll wrap up here briefly because I know I've already gone over time. But some of the key findings, as I mentioned, both models, they perform significantly better if we count for overdispersion in the process model. And in model 1, another thing that we tried to test is a negative trend in transmissibility over time, and there's various explanations of why this might be the case. In particular, one effort that was done in Haiti is once they found some cases, they would send basically health workers to educate the people in the surrounding community about cholera and sanitation, and they would vaccinate individuals that were closely tied to the case. Of course, that wasn't present at the beginning of the epidemic, but those efforts increased over time. So that's one possible explanation why the transmissibility decreased over time. Finally, our study also confirmed previous understanding of the importance of rainfall in Haiti as a driver. So I mentioned previously we had that very flexible 6 baseline basis for the transmissibility. And if we analyze what that looks like, that's this dotted line here is the B-spline basis, the effect of that over time. And the solid line is the average amount of rainfall. And we see that it actually follows quite closely that this very flexible B-spline term for transmissibility rate follows quite closely the rainfall in Haiti over that period. All right, I'll wrap up there, but first I'll do a couple of acknowledgments. First, from this study that I mentioned, Lee et al., there's a lot of people involved with that study. We were in contact with quite a few of them, and they shared a lot of their data and code with us that enabled us to look at this result, and also some fellow students that helped were part of this project as well: Kevin, Noah, Anna, and Josh. All right, thank you.